Welcome, everyone. Um, my, oh, all right, maybe that feedback looks like it's come and gone. Welcome, everyone. Thanks for joining us. My name is Andrew Sachs. I'm at the Department of Psychology at Oxford. And it's my great pleasure to introduce our speaker today, Professor Linda Smith. Linda is the Chancellor's Professor at Indiana University, and she has had a long, distinguished career at the forefront of developmental psychology, with many awards to her name. Just to name one, she recently was awarded the Norman Anderson Lifetime Achievement Award from the Society of Experimental Psychologists. So I'm very pleased that she's here with us today, and she'll be talking about learning from the infant's point of view. And just before we start, in case you're joining us for the first time, there's a chat that you can participate in and ask clarification questions if you have them that you think other participants might be able to help you with. But there's also an ask a question button, and if you click that, you can pose questions, which I'll be monitoring, and I might pose some to Linda as she's going. So with that, floor is yours.
All right. So good afternoon, everyone. I am very glad to be joining you in this forum. And so to begin here, all right. So learning, adaptive, intelligent change in response to experience is a core property of human cognition, a core function of the human brain, and it's certainly a long-sought goal of artificial intelligence. But here's what I want us to think about. Although everybody's interested in learning, not a lot of people who are interested in learning are interested in babies. But any theory of learning worth its salt should have something to say about how infants learn all that they do in the first 2 years of postnatal life. Babies start out knowing very little with very few skills. They learn about objects, they learn about their bodies, they learn about the social structures of their culture, they learn a specific language, and quite remarkably, they learn how to become robust and rapid learners in a variety of different domains. So as a starting point for my talk, I'll mention two examples of the remarkable abilities to learn that are evident in 2-year-olds. And we actually know a fair bit about these, and they are learned abilities. They are not there from day one. They develop and change over time. So let's take the example of face recognition. Let's say you're the parent of a 2-year-old, and you have some family event, a reunion, and Uncle Eddie shows up at this reunion. Now, your 2-year-old has never seen Uncle Eddie. He doesn't show up all that often, but Uncle Eddie shows up this time. He's a funny guy, okay? Your 2-year-old spends a lot of time interacting with him. And here's what the deal is. One day of Uncle Eddie at a family reunion, if Uncle Eddie shows up 6 months later, it's highly likely your 2-year-old, maybe now 3-year-old, will recognize Uncle Eddie, even if he's a little bald or a little older, got a hat on, okay? Your 2-year-old might even be able to go into your old wedding pictures and look back and find Uncle Eddie 10 years younger than he was when he met him on that day at that family reunion. That's one-shot learning. Uncle Eddie, one day, a lot of Uncle Eddie, but he'll recognize Uncle Eddie the rest of his life, pretty much. They don't just do this for faces. 2-year-olds do it for objects. If you have some child who lives in some urban place and hasn't actually seen many tractors, you come out to some nice place like Indiana, where I am, and there you see your 2-year-old sees working in the field a big John Deere tractor. He watches it, you talk about it. This is something every parent will recognize. That 2-year-old will go forward from that day and will recognize tractors pretty much in a mature adult way, accepting Massey Ferguson's antique tractors, drawings of tractors, toy tractors, but rejecting backhoes and Jeeps and trucks, okay? One-shot learning of categories. They become very, very rapid learners of new categories. Need a single example. So how do we explain how babies do this? How they learn all that they do? Well, learning depends on both the learning machinery and the training data. Now, most people who worry about learning, both in psychology, in neuroscience, and in artificial intelligence, worry about the machinery. But what I want to talk about today is the training data. The training data define the task to be solved. The training data contains the knowledge to be learned. And really, it constrains the possible machinery, the kinds and classes of machinery that can learn from that data. Really, we should start with the training data. So what I'm going to talk about today is work we've been doing for really over 10 years now, trying to capture the visual experiences of babies from their own point of view. We put head cameras and head-mounted eye trackers on babies to try to capture visual experience at the scale of everyday life. We've done this in multiple ways. What we call the multisensory experiments, where we wire babies up that get head-mounted eye trackers, motion sensors on their bodies, high resolution, sort of naturalistic. The toy room, which is in the lab, so some control, but free play. And then also using head cameras, day-long recordings at home, which we've collected in the United States and also in under-resourced village in India. We have lots and lots of egocentric images from babies. And so that's what I'm going to tell you, what we're learning from that. And most of this work, I'm going to concentrate on what is called the HomeView Project. This is funded by the National Science Foundation, who very bravely funded us for this work and is still funding us, and also by the initiative at Indiana University known as Learning Brains, Machines, and Children. We have a corpus of 101 infants, 3 weeks to 24 months. We sought day-long recordings, but some babies only contributed about 4 hours. Parenting is hard. And these are the data. Oh, the thing is, we just put head cameras on babies. There were no experimenters present. They were embedded in hats. And we told parents we were interested in the baby's visual experiences, that they were not looking at any kind of particular activity. We just wanted a day of visual experience. All they had to do was make sure their baby was awake and that the head camera was over the nose, okay? So highlight one from these data. The first thing is that the data for visual learning changes dramatically with the development of the child. Each new sensory motor advancement changes what infants experience, yielding a curriculum, a changing input for visual learning. And this is a set of videos that were constructed by Jason Gold, one of my collaborators. And at the top is what we call sparse images. You don't have to care about that. At the bottom is what we call ordinary images. I'll talk about those, why we have these two groups later. But if you look first at the 0 to 3 month old images, top to bottom, these are just samples, okay, every 5 seconds. And then now move your eyes to the 6 to 8, top and bottom, sparse and ordinary, and then over to the top and bottom, sparse and ordinary for the 11 to 12 month olds. If you just look at these, you can see that the contents and the visual properties of these images change dramatically with development, okay? That's what we want to understand. All right. So one of the first things we discovered was, or looked at, was that the frequency of faces in these babies' images changed dramatically with age. So what you see here on the y-axis is the proportion of frames with faces, and age in months on the bottom, from infants from about 4 weeks to 11 months. Each dot is a single child, and this is one of our earliest studies, first publication from HomeView, had 3,000 images. Each dot stands for 3,000 images or so. So what I want you to see here is that the frequency of faces declines dramatically with age. That may not look like such a dramatic change to you, but frames are time. And if you look at the youngest babies, what they are seeing are faces 15 minutes out of every waking hour. By the time you're reaching 11 months, babies are seeing faces only about 6, 8 minutes out of every hour. The nature of the faces these babies see also changes. The proportion of faces that are within 2 feet of the head camera are, that is, faces that are very, very close to the baby, are very frequent for young babies, not so frequent for babies that are older. And if you look at what's happening here, but I'm going to say more about this in a little bit, but what here is we're trying to show you what this relative frequency of faces might mean. So on the y-axis, what we've estimated is what would be the cumulative face hours a baby would experience from birth to 12 months of age, and that is shown in the yellow, cumulative face hours. And then we've estimated their total visual experience and their cumulative waking hours, that's shown in gray. And what I want you to notice is that for babies under 3 months or so, 4 months or so, faces within 2 feet of the baby make up a substantial portion of all their visual experience. Okay? A substantial portion of all their visual experience. Let's just hold on to that idea as I move forward to the next highlight from the home view data. And so this is highlight 2, and that is that early environments may be very tightly constrained by evolution and by development itself in the kinds of input, kinds of visual input that babies get. So these are data that we have collected in Bloomington, Indiana, and in Piyador, India. These are very different developmental contexts. Bloomington, people live in houses that average 2,500 square feet, and there are on average 2.1 people per house. The babies in Piyador, India, are growing up in a community in which houses are averaging under 500 square feet, and which there is on average 4.2 people living in those houses. And much of the life in Piyador, India happens out on the street cooking. Everybody's kind of isolated in Bloomington from one another. May not be such a good thing, but it's the way it works. All right. So what we've done is we've collected head camera data at home, no experimenters, same cameras, the whole bit in these 2 communities. And first, what I want to tell you is that there is very little change in the cumulative amount of faces in India, which is shown in orange here, or in the US shown in blue, using that graph that I've shown before. And there's considerable overlap in the first 3 months. And the other thing that I can show is he's just showing the curves across the data, the 95% best fitting lines to development, is that babies in both cultures see primarily frontal views. The mean distance of the faces that they see increases with age in both cases and is very close for the youngest babies. And for children in both cultures, they see principally only 3 individual faces, although the variety of faces increases more dramatically with age for children in India than in the US. But what I want you to notice here is that the properties that we've characterized in US babies for infants under 3 months of age pretty much generally characterize the nature of face experiences for babies in Piyador, India as well. Now, why is this the case? Well, there's a long literature that has shown that very young babies, babies under 3 months of age, are biased to look at high contrast, low spatial frequency figures of any kind, and particularly high contrast, low spatial frequency images that have face-like properties. In fact, very young babies would rather look at a caricature of a face, a smiley face, more than they would a regular face. So babies at, excuse me, babies at very young ages are strongly biased to look at close frontal views of faces. And of course, parents like being looked at, so they hang around, and these babies are in need of great care, also keeping parents around. So the visual system early on, probably cross-culture, is getting a dense diet of low spatial frequency, high contrast, two-eyed faces, okay? We also noticed in our home view data that babies under 3 months of age also are biased to look at, these are what we call the sparse images, images that don't seem to have very much in them. What I've shown on the side here is a sampling from one 9-week-old infant. It's sampled every 5 seconds, images over a 4-hour period for this 9-week-old infant. And what you can see is there's long periods of looking at a light in the ceiling, the edge of a wall, high contrast, low spatial frequency, simple structured images. And what the figure there is showing you on the side is comparing the frequency of images, comparing the RMS contrast, that is the amount of contrast, and the slope of the function that relates contrast to spatial frequency on the y-axis. The steeper that slope, the more the contrast is concentrated at the low spatial frequencies. And as you can see, in 3-month-old infants, there is a strong, strong bias for looking at images that have high contrast and where that contrast is concentrated, okay, at the lower spatial frequencies. So let's think about this. If we put together faces and these simple Gabor-like filters that babies seem to look at, under 3 months, about 25 minutes out of every hour, okay, is a high contrast, low spatial frequency face or simple edges, the edge of a door, a light, okay? I think the question we want to ask ourselves, if this is constrained and pulled in by Mother Nature, little variability, okay, development kind of forcing it, what is this early, temporary, not lifelong, temporary bias, faces, high contrast, simple edges, images, teaching the visual system? I'm going to come back to that as well. Okay. So here now, highlight 3. There's not just a curriculum of different kinds of stimuli. There also seems to be a curriculum of visual tasks that is creating developmental niches for solving different classes of visual learning problems. So I've shown you, these are other data on faces. On the top thing up there at A, it's the proportion of images with faces for infants from 1 month to 24 months, declines, as I've told you. And the next slide shows the proportion of images with hands for these same babies, again, from 1 month up to 24 months. And what you can see is it's not simply that faces decline as if people stop hanging around these babies. No, people are hanging around. It's just that babies are looking at different body parts. There is a sharp developmental shift from a lot of images containing faces to a lot of images containing hands. The figure C, which shows the subtraction of faces minus hands, is just really to illustrate how developmentally ordered this is. These are all different babies. Each bar is a different baby, different house doing different activities, 1-day sampling. And what you can see is that there is an absolute systematic bias from images containing more faces to images containing hands. Now, the thing about hands is that it's really not maybe just hands that this is about. It's not, the images with hands that babies are seeing are not like hands waving in the wind. At all ages, more than 70% of the hands in view are touching the object. So these egocentric images, these visual experiences that are dominating in older infants are about hands instrumentally acting on objects, pretty much their own hands and other people's hands. So The contents of visual experience, this is just one example, change from being dense with faces to being dense with hands acting on objects. These are creating data sets that are about very different learning tasks. One about learning to recognize individual people. We'll do that first, and maybe about some other things as well. And one about learning about visual objects and instrumental acts on those objects. So, I mean, I don't have an answer for this, but let's just think about this for a moment. This is the question I think we need to ask. We have a whole visual system that from the lowest levels to the highest levels is first learning about high contrast, low spatial frequencies, and faces up close, two-eyed. And then it's learning about, and then the same visual system, after it's solved all those problems, or made a lot of progress on those problems, then it uses whatever tuning and learning of the visual system from low spatial frequency and faces, that then is somehow the basis from low to high level in the system about learning about objects and manual actions on objects. Reflect on that a bit. It's an odd thought, but just keep reflecting on that, okay? So here's highlight 4, and this is where I think the work will be going in the future. There are not just developmental changes in the high-level content of these experiences, faces, hands. There are also systematic correlations between low-level and high-level visual properties, and those correlations change with development. So this is a figure where I'm trying to summarize all that we're trying to do, both the work we've completed and ongoing work at the moment. And so we have development, babies and what they can do are changing from early infancy up to the first year of life. We look at the images, daily life, day long, see all kinds of changes in their content. That's what's illustrated in the middle. These are either data we already have or our best guesses from the data that's coming in. We have faces declining with age, hands increasing. We have this period in the middle of infancy where the visual world is just cluttered, a lot of energy at every spatial frequency. And of course, we have what's ever happening within the visual system. Okay. And what we're finding is that there are correlations between the low-level visual features and the high-level content that change with age. Let me give you one example. So these are brand new data. I have not been talking about them, so this is new. But what I'm showing here is the medium contrast at each pixel location across 60K images per age group. So contrast at each pixel location for 0 to 3 months, 4 to 6 months, 7 to 9 months, 10 to 12 months. What you can see in these images, okay, is that contrast is sort of wandering to the center of the head-centered image, okay? So where contrast is sort of more all over the place for the youngest babies with development over the first year of life, high contrast is being put in the center of the image. We also know that if we break this apart, we can see that for the youngest babies, contrast is more centrally concentrated when they're looking at faces. But for the older babies, contrast is more centrally located when they are handling an object. Okay. So what's happening here is that the low-level statistics in the input, since all of us perceive better when we have high contrast, and we perceive better when whatever we're attending to is at the center of our head-centered image, which is where the eyes like to look, that low-level statistics in the input are organized to bias learning about different classes at different points in development. So that's the kind of niche idea, and I think it's an important one. But it's also the case that every image, every moment of vision is carrying information pertinent both to low-level features and high-level features. And we know that the visual system is being tuned and trained from day one by the input that it receives. So the faces those babies are seeing up close and early are not just about the faces, okay? They're going to be about V1 and V2 in the middle levels, okay? We also know that there are strong recurrent connections, and particularly strong connections down to V1 and V2. And these develop together with directional influences that are evident in infancy. Here's my thought, okay? Here's why I think that these changing correlations of low level to high level content may be the most important thing any of us could work on. There's a lot of discoveries now about the recurrence in the cortical visual systems and about top-down processes influencing low-level visual processes, putting gains on signal that appear to play a really big role, okay, in object recognition. The data just keeps coming in on that, okay? But none of that will work. You can't have top-down processes affecting the perception of high-level content by putting gains on what's coming out of V1 and V2, unless there are some correlations in the information across those levels, okay? I think this is what we really need to concentrate on if we want to understand the development of the visual system and how we become such amazing visual learners. All right, highlight 5, I'm coming close to my end here as we have only 6 highlights. All right, so highlight 5, massive experience with just a few individual things and rare experiences with many things characterizes all aspect of visual experience from the youngest babies to the oldest babies. The distribution of experiences are not normal, they're not random, they're not uniform. So you can see this with faces. So just 3 individuals account for most of the faces, okay? Although there are many faces to be learned, experience is massive with respect to a few faces. So shown in the figure here on the y-axis is the proportion of frequently appearing faces. On the x-axis is age in months, and as you can see, these are for babies in Bloomington, Indiana. The 3 most frequent faces, let's say mom, dad, and grandma, okay? The 3 most frequent faces characterize over 80% of babies' experiences across the first year of life. The same pattern is observed in India, particularly for the youngest babies up to about 4 months of age. And then the babies in India get more variety of faces. But early on, we are building a face recognition system with very few faces. And for the India babies, the top 3 faces still count for about 60% of all faces, okay, by 12 months of age. Okay. Just think about what this means, okay? It's contrary to what most people think about overfitting or the role of variability in learning categories. We actually become expert at faces by first becoming expert at a very few faces. The reason why we can recognize some new person and learn his face and form a strong memory of that when we're 2 or 3 years of age is not because we've learned lots and lots of faces. It's because we're expert at a very small number of faces. This same kind of distribution characterizes our experiences of individual objects. So most people who would think how you should teach anyone about what a cup is would think that you should show them a whole variety of lots of different cups, okay? Every kind of cup you could imagine, train them. This is a cup, that's a cup, that's a cup, so they could find out what's the same about cups. But babies' experiences, they have massive experience with individual objects. So we have these are data, all these sippy cups that you're seeing in the center there. These are data from one child, 18-month-old, who contributed about 8 hours. He was one of our big contributors, got close to 8 hours of visual images in a single day. And here's the thing that's interesting. This sippy cup that is in every one of these figures shown here was in 40% of those child's images across 8 hours. 40%. That child saw that sippy cup in its own hands, in its mother's hands, upside down, half covered by a blanket. No other cup was in that child's images more than 0.01%, okay? There was a Starbucks cup somewhere and there was a mug somewhere, but very rare over those 8 hours. That baby is learning about cups with a huge emphasis on one sippy cup, okay? So this is true for faces, it's true for individual objects, it's also true for common categories. So these are data. We have a second paper coming out on this. First paper was published in 2016. And what we did in both of these studies is, again, from home view, is we are looking at the images collected by 7 to 11-month-olds. This is a very interesting age because these babies do not talk, but they are clearly learning about visual object categories, and so that we would have certain kinds of categories, since all categories are sparse in the scale of real-world experience, so we'd have some repetitions. We focused on what we call meal times, but really they are images that had any kind of food or dishes in them or anyone eating. And what we did was scene to text coding. And the main thing we want to tell you is that when people coded this is from the first set of results. We had people code name the objects in each image. They could name up to 20 objects. We trained them what basic level categories were, and they're supposed to only give us basic level categories. Well, for the first study, the 2016 study, the coders gave us over 782 unique basic level object categories in the entire set of images. But most of those 700 plus objects occurred very, very infrequently, almost not at all. But a very few categories, mealtime, eating categories, a very few categories were pervasive, were in all the images, many images from individual children and many images across all the children. And these early, highly pervasive images also corresponded to the first object names that babies learn. Now, these babies might not know those names yet because they're 7 to 11 months old, but they correspond to the first normatively learned object names. So what is this pervasive experience of a few categories, cup, spoon, table, chair, and a few unique objects, the child's own individual sippy cup, doing for visual learning? It seems to me this is probably doing the really big work of segmentation, of finding things in clutter, of building strong visual memories. And of course, the next question we want to understand is how all this might relate to the one-shot learning of whole categories, okay? So that's the question I think is another big question we need to answer. What does this extremely right-skewed distributions of individual objects and of categories, what does this data structure mean for how children learn to become one-shot learners of things like Uncle Eddie or tractors? Well, as I said at the beginning, learning depends on both the learning machinery and the training data. And the training data defines the task to be solved, and it determines its optimal solution. So everything I've just told you thus far, what it says is that the data for learning to be a one-shot learner in children is massive amounts of projected images from a small subset of individual objects and for a small subset of to-be-learned categories and a lot of much more sparser, rarer experiences of other individual objects and other categories, okay? Here's my conjecture. I think the solution and the answer to how children become one-shot learners lies in the unification of the two core problems in visual object perception. The first core problem of visual object perception is how we recognize, that should be an and, how we recognize an individual object as being the same thing despite the continuous and marked variation in the image projected from that thing to the eye, the image that we capture in head cameras and in the scene cameras from head-mounted eye tracking. The second core problem in visual object perception is how we manage to recognize the many thousands of categories of things and their indeterminate number of instances, and how we continue to keep learning many more categories and generalizing new categories from those minimal instances, okay? So here's what I think that right-skewed distribution, I think it solves both these problems for us. Here's my hypothesized path. I think the packets of toddler-generated visual data, the egocentric images we're capturing with the head camera, teaches the visual system how to recognize an individual object, the sippy cup, across variable and challenging contexts, being held up close, partially occluded from an unusual view. Then I think this learning generalizes, leading to the robust recognition of shape-similar objects. Okay? So now they can recognize not just their sippy cup in challenging contexts, but they can recognize shape-similar objects in challenging sippy cups. Their doing of that, by the way, notice, and their realization that the two things might both be called cups, even though they've had minimal experience with the second sippy cup, is actually one-shot learning. They learned one sippy cup, and because they learned about its structure, it generalizes to things with the same geometry, because that geometry determines what's in the projected image. I basically think one-shot learning is probably the pathway for all object learning. It's about learning the deep regularities in the projected images from single objects, and that leads to generalization to other objects with similar geometry. I think this likely leads to nuanced knowledge about objects as well, which is a current failure in artificial intelligence, but I'll leave that behind. All right. So, highlight 6, all right? Everything that I've told you, every little highlight that I've given you, every little result here, from the developmental changes in the input to the properties, low level and high level of that input, they are really about the properties of the baby's body and the behavior of the baby. The images in front of our eyes, the data for visual learning, depend, because the eyes are in the head, depend on our body, our posture, and what we do with our body. Behavior creates the data for learning. And it is the changes in the baby's body and behavior that leads to the curriculum. So I have this little image here. You just watched it before, but look at this. This is the toddler niche, and that's what I want to use for this example. Look at this child looking at this object. Slow, beautiful image, okay? Foreground, pulled out from everything. Centered, mom comes over, says something nice, okay? All right, whoops, down here. All right, so now I'm gonna, for this last little bit, I'm going to present data from the Multisensory Project. This is where we bring kids into the laboratory. We use dual head cameras are now in all the work, dual head mounted eye trackers on both the mom and the child. We have motion sensors. Everybody's wired up every which way, multiple room cameras. And this work, we focused on children from 9 to 36 months. And I'm just going to present you about toddlers, 18-month-olds, okay? So children over past their first birthday spend a lot of time handling objects and a lot of time looking at objects in hands. You see just lots and lots of head camera images that look like these images here, okay? So one of the questions we asked is, are these optimal moments for learning object names and for learning about visual object categories? So we spent a fair bit of work trying to answer that question, and I want to tell you about two studies to begin with. They're pretty much the same. It was a pretty interesting result, so we replicated it with slightly different methods, but I'll just treat them as one big study. What we did in this study is we brought parents and children into the laboratory, again, all wired up, and they were to play with 3 objects at a time. These objects were novel objects, and we taught the parent the names, the novel names for these objects before play. The parent was never told the child was going to be tested on these objects or that we were only or principally interested in the learning of object names, but after the play session, we tested the child for whether they had learned the object names or not. We used a 3 alternative forced choice task as illustrated here. We would say the object name, where is the modi, where is the modi? And in one study, we measured eye gaze. In the other study, we had trained the child to actually go get the objects, okay, and use hand responses. So what we want to know is how the naming moments associated with learned names differ from the naming moments not associated with not learned names. So what we did is we took performance on the word learning test, and we divided each object into one where the child had learned the name and it's linked to the visual object, and classified the others based on the child's individual performance as to an object name that was not learned well enough to show up at test anyway, and linked to the visual object to show up at test, okay? And then, so you got 2 piles of objects for each child, those that were classifying as learned and those that were classifying where they learned about the object and those where they didn't show learning, okay? Then we went back in and we looked at the visual properties of naming moments during play from the child's point of view, okay? And asked how the visual properties of the named object when it was learned differed from the visual properties of the named object when it was not learned. All right. So let me walk you through this figure because it's got a lot of parts to it. So on the y-axis are visual properties of the objects. I'll say more about those in a minute. On the x-axis is time. Right here in the center, there's a little blurry thing, I'm sorry that it's blurry, that says UTT, that's utterance. That's when the naming moment happened. And then we're going to look at the visual properties for up to 10 seconds prior to that naming moment and for 10 seconds after that naming moment. So the time in seconds there, that goes 20 seconds plus the timing of the utterance, okay? 10 seconds before, 10 seconds after, all right? On the left-hand side are the visual properties as a function of time for object names that were learned by the infant, and on the right-hand side for object names that were not learned. Within each little space here, the blue lines show the properties of the named object, the target, and the red line shows the properties, the mean properties of the competitors. The patterns of results are the same if we look at the strongest competitor, not just the mean properties of the competitor. But that's what I have here. So what do I want you to notice here? If you look, the top one is the object size on the y-axis, and this is measuring how many pixels, what percentage of the field of view is being taken up by the named object versus the competitor. And what you can see when object names are learned, the visual size of the target is much, much, much larger than the visual size of the competitors, and that advantage is not so great for the targets. Moreover, I want you to notice that the visual size advantage is enduring in time over 4 to 7 seconds, okay? The bottom set of figures show the overlap of the named object with the center of the image. And as you can see, when object names are learned, the named object, the visual referent, tends to be more centered in the visual field than the competitors. And also because it's more centered in the visual field than the competitors, it is also farther away from in the visual field the competitors. And that's not so much the case when object names are not learned, okay? Now we've been studying these properties of what creates visual learning and the learning about object names, and we know a great deal about the role of the baby's body, and I just want to summarize a bunch of results here for you. So first of all, we know that babies are more likely to learn about a visual object and to link a heard name to that visual object when their head is stilled, not moving, okay? They are more likely to learn the name of to learn the name and remember a visual object when they are holding the object than when the parent is holding the object, even though the parent may often create, okay, visual images at the naming moment by holding the object close to the child that looks like, has the same size properties and centering properties as when the child holds the object. Why does child holding matter? Child holding matters because when the child holds an object, it stabilizes the head, and the advantage of the visual object over competitors is more enduring in time, lasts a longer time. When parents hold the object, even when they create the same image, same advantage in size, it is not as lasting. It's a briefer event, okay? So all these unlearned object names over here, where they're from the just previous slide, they are often ones where the parent is holding the object. The temporal advantage goes away. We also know that when babies are holding the objects, they're not holding them up there like a picture, okay? They're not like just stilled for 4 seconds at an object that is not changing. They are moving their heads and their bodies, and they are getting different images of those objects, different points of view. It's dynamic information about the object. We also know that holding the object is more likely to lead to centered gaze within the head-centered field of view, which also appears to be, we think, an important advantage to learning. But these are all properties of the baby's body. And the thing I point to make larger to the other parts, the beginning part of the talk, these properties of the baby's body, they're properties of an 18-month-old body. They're not properties of a 3-month-old body or a 6-month-old body. This is the niche for learning object names and for learning about visual objects, 18-month-olds, okay? Everything they do brings that high contrast, centered information about a single object and dynamic views of those objects. Their bodies are made for learning about objects and for learning about object names. All right. So learning depends, this is where I began, on both the learning machinery and the training data. And what I've told you is that when you look at the training data from the infant's point of view, what you get is a curriculum of experiences and tasks, a series of developmental niches. We get these extremely right-skewed distributions because our experiences are in time and they're constrained by the physics of time and space. We see what's around us and what we use all the time, and constrained by development and by behavior. And the last point that I was making is that this is really all about the body, okay? At the time scale of real-time behavior, okay, the brain, the baby's behavior, and the environment jointly work together to create the data for learning. So what the internal structure of the brain is generating behavior, which generates the input and changes in the world and turns that back on the brain, okay? So they're tightly coupled learning systems in real time. Behavior is generated by ongoing neural processes. It comes back in, it changes what's happening in the world, sends back sensory information, and modulates activities in the brain. And over time, here's at the time scale of development, the brain, the behavior, and the environment are all changing and co-developing. This is really a developmental system about the co-development of what generates intelligence and the data, the data for growing intelligence. And they are deeply coupled in real time and changing, I think, in ways that will eventually tell us how a great deal new insights about how all this works. All right. So all of you, I sometimes say this at the end of my talk, so I'll say it here. All of you should become developmental scientists, okay? Any theory of learning or of neural development or of behavior worth its salt should have something to say about how infants learn and manage to do all they do in the first 2 years of postnatal life. It is perhaps the most interesting question and the most important question any of us can address. All right, I want to thank all my collaborators. There are many, and most of them are much smarter than me, including my former students and postdocs and the folks currently in my lab, and of course, the people who have supported the work. Thank you very much.
Thank you. That was absolutely fascinating. I wish we could all clap for you, but it'll have to just be me, I'm afraid. And now I'll pose some questions. If you have your own question, you can ask it through the question answering system. You can let me know if you want to pose it yourself, or if you'd like me to say it. So to start off, Tim Vogels have a question. Yeah, if you switch back.
Okay, if I unshare in some way.
Do.
Oh, I can see the side thing now, if people don't mind. Okay, I can see the side thing. Okay, good.
Yeah.
And then I can bring it back up, I guess, if we need. Okay.
Yeah. Okay, so the first question is asking whether you can test and assess the generalization abilities of children for the objects that they've been exposed to in terms of the hierarchy of categories. So for the sippy cup is a more specific version of a cup, which is a more specific version of an eating utensil, maybe. And can you link that to the exposure frequencies for these categories?
Okay, that is actually a really important question. And Elika Bergelson has a study, I think it might have been published in Infancy, but where she asked directly, one of the questions that I think that follows from this, she asked, do young babies recognize their own sippy cup, let's say, or their own shoe better than they recognize other shoes, okay? And her infants were, I can't quite remember the age, but they're youngish, I think prior to a year, okay? And the answer was she could find no differences for highly experienced versus novel objects. This is why I think that really visual learning for infants, contrary to everything we've always been thought about, overfitting, and you need lots of examples, I actually think we've got the question all wrong, okay? That what babies are learning is when they learn about their own sippy cup, they certainly are learning their own sippy cup, they want their own sippy cup, but they're also learning about how, because they have so many images of this, massive, okay? Different, varying continuously in time, they are learning all the principles behind what their sippy cup can look like when included, when near, when far, when upside down, when in shadow. These are the laws that give us individual objects, but they're all constrained by the geometry of the object. And I think they can generalize across it. I think all learning is immediately pretty much one shot. There's no overfitting, that they would recognize a blue sippy cup immediately and maybe a Starbucks cup, okay? Certainly hearing names of things is helping, but I think that we've got the idea wrong about generalization, okay? That we're thinking about it from an adult point of view about building category boundaries, whereas what the visual system is doing is learning the principles of recognizing objects from the continuous flux of the retinal input. That's my thought. But yes, we are also trying to do in the way that Bergelson, that original study did, is do training studies with babies. They were stopped by COVID, but the purpose of those ongoing studies was to do specific training with very specific objects and then ask how far the generalizations would go and what kind of properties they would base those generalizations on. And it's a very important question to ask. It is the next one.
Can I ask a follow-up to that before I go on to some of these other questions, which is, I mean, if you brought this to a machine learning researcher, I think they would probably say, how can you know that, the cup, you could have thought, oh, it's just anything green and blue is my sippy cup, right? So do you have a sense of what's imbuing these geometric biases, or what do you think algorithms might need to have that more geometric focus rather than?
Okay, I think we can do it with, there's two ways that you can represent the generative structure of a sort of three-dimensional shape. You might have some kind of three-dimensional shape representation. You could also do it just in terms of, some complicated n-dimensional similarity space where you've just shifted the similarities of things around so things that have the same shape are sort of near each other. That is, they don't have to actually abstract some internal representation of 3D object. I don't know which of those approaches are right. The brain appears to do a little bit of all of it. But I think they've got the basic question wrong, the basic computational task wrong. And I'm working on this right now with a group of people. But the question that the way most CNNs and everything that's doing a really good job now works is they're trying to find boundaries between categories. And they're trying to learn the labels of categories. They're trying to discriminate, is this a sippy cup or is this a chair? Is this a sippy cup or a vase? Is this a sippy cup? I don't think babies are forming category boundaries. I think they're learning, what is my sippy cup? Okay, I think the computational question is different. We have made a little bit of progress actually using very standard CNNs, popular, but altering their task. And we have some evidence suggesting that maybe redefining the task will make one-shot learning of the way I'm describing it, where you're just generalizing to things that have similar properties, okay? Pretty straight up. Not hard. I think it's the definition of the task, not the deep learning network structure or whatever. It's a task.
All right, and so moving on, Charles Maurer asks, it's not surprising that holding an object makes it easier to learn about than merely seeing it, because holding the object adds a sensory system. Do you have a...
Yes. I think there's two ways to think about that. He's absolutely correct. And every part of the learning system is likely a complex system where we have multi-sensory inputs, we have behavior acting on the world, changing what happens next. There's not going to be any necessary insufficiency that it's just the pattern on the retina, okay? So I'm not making that claim at all, okay? However, it is also the case that what we see always depends on behavior, and we are always altering visual input to make it easier to see, okay? Babies just do, well, toddlers, not young babies, but toddlers just do more of it. So every time we shift our gaze, we are basically making the object we want to attend to a better competitor against other competitors, because we put it at the fovea, where we have greater sensitivity to greater acuity and greater sensitivity, and everything else is a little less good, okay, because it's not at the fovea. So every time we look, that's like core. Let's make it a little easier to see, okay? I want to look at something, I want to look at Andrew on my screen, who's very little, okay? Well, let me make Andrew easier to see, all right? All babies are doing is the same thing, okay? except they don't just move their eyeballs. They say, let me make it easier to see. They move their head close. We also all do that. We walk over to it. It's a core part of vision, okay? Is that we change the pattern. And so I think that is part of what they're doing. But absolutely, yes. I am sure there are, if we want to go to, predictive coding and we want to go to, there's all other kinds of things going on here, most definitely, because they are making those data in time and they have multimodal consequences, for sure.
Picking up on that, bringing it in front of your face sort of point instead of moving your eyes. A question here from Patricio Oreo. The data is amazing. I'm surprised that all of this works without taking into account eye movement and eye fixations. How much do infants move their eyes, and how much more do you think we could learn if you had that data?
Actually, I want to say we have a lot of that data. We have been doing massive amounts of head-mounted eye tracking in the world with babies. The thing is, you can't do day-long recordings with that because it could poke their eye out. And the kind that work through glasses do not work for young babies. But we know a great deal. And I could have done a whole talk on that. But here's the thing. Everybody, little babies, toddlers, you and me, we look at the world principally with our gaze centered in a head-centered frame of reference, okay? When we're looking at screens, we dart our heads about a little bit. But if we want to look at anything for any duration, we turn our nose points also to the object. So all the work of people like Mary Hayhoe, Kingstone, a bunch of others who've looked at head-mounted eye tracking, and our work and Karen Adolph's work and Franchek's work, looking at babies, everybody. If you're not looking at a screen and you're not in a headrest, okay, you really want to look for any duration beyond, 25, 50 milliseconds or so. Certainly anything beyond 500 milliseconds, you want to look with your nose and eyes pointed in the same direction. So I think actually there are guys in AI who are developing systems where you can do head-mounted eye tracking without any eye camera because it is so predictable where the eyes are from the scene properties and from the nose. It's very, very predictable. So actually, I don't know that we need it, but everybody wants you to have it, so we definitely have it too.
Interesting. All right, and a question from Matthew. Do you think children who are diagnosed with autism in later childhood showed different sensitivity or interest to human faces as infants? The data you collected may allow a prospective study to see if there is any such correlation.
Oh, I'm sure they show differences. And they're a very complicated story because they have all kinds of sensory motor differences, including in eye movements, including in head movements, including in body movements and their timing. And, where the origins of these lie, the, less often looking to faces or whatever is, I think, probably a complicated story. But yeah, I'd take the evidence for what people show it to be. My colleague Chen Yu has been collecting data with autistic children in very similar contexts to what we've done here. And, there are differences that matter. Okay. And I think the answer is complicated, but yes. Okay.
I guess it seems like a lot of the evidence you presented, you're talking about shifts in the curriculum, like the nature of experience that an infant is receiving. But I mean, isn't it also possible to see developmental transitions that even with a static environment, you might also see children passing through different types of regularities in their performance? So I guess I'm curious why curriculum seems to be the core focus rather, or maybe it's not the core focus. Maybe you think they're both not mutually exclusive, but what you think sort of just the intrinsic learning dynamics would be even with a fixed set of environmental statistics.
So here's the thing about development. And if you only think about adults, I think people miss this, okay? Development creates real changes and you can't go backwards, okay? You actually do need to sit up before you can stand, okay? Standing builds on the progress of sitting up, okay? You actually need to sit up before you're going to do any kind of interesting goal-directed actions on objects or generate different views of objects, okay? It's more, the system fundamentally changes, and what happens downstream builds on what happens before. So in some sense, you can think of this, and I can make it sound less interesting, but certainly you're better off learning multiplication after you've learned to add, right? Because it's kind of, so this order, okay? So we have what's happening in real time, which is really interesting and probably has lots of generalities beyond development. But what's happening in the first 2 years of life is a very systematic change in what babies can do, okay? And it's very systematic, okay? You're gonna sit, you maybe not crawl, not everybody crawls, you're gonna stand up, you're gonna walk. Walking and crawling, that actually builds breathing capacity that helps you utter words. It plays a role in your ability to even talk, so your parents will talk more back to you. These things are highly constrained, okay? But they're highly constrained not because you have inbuilt, that you're going to speak English, but because they create an environment and they can create an ordered environment. Everybody is so interested in batch statistics because it's easy to use that they don't have algorithms that actually think about how to build and change a system. Really, I kind of think of Rodney Brooks' subsumption models as being actually closer stories, maybe not in their details, right? But closer stories to what development has got to be about. You build one little system and then you incorporate it into the next achievement. And if we're going to understand it, we really have to understand it that way.
Interesting. And one final question before we let you go. So you brought up, I think you at some point referenced these studies by Margaret Livingstone showing sort of similar face development in monkeys. I'm just wondering what this perspective would mean for other animals. Like, do you think visual development always has to have this kind of progression, or would you see it as possibly being different in different species?
I think it'll be fundamentally different in different species. So one of the interesting things about human beings, okay, is that we have an extended period of sensory motor development. Many animals, they're born and they start running around and gathering food, okay? Many mammals, okay? Horses, dogs move much faster, right? Babies, human babies are forced to sit mostly, sit in their little pumpkin seat and look and listen to the world for 3 to 5 months with very little movement, okay? I don't think this is an accident, okay? I'm pretty sure it's not an accident, okay? And I think one of the things is, what is the computational problem being solved by that, such that then movement then opens up other kinds of experiences that are building on top of these early experiences, okay? But so certainly other primates show similar properties, but not completely similar, but show similar properties in their early development, although much speeded up. But it doesn't have to be that way. Lots of mammals don't do it this way at all.
Great. All right. Well, thank you very much for your talk and your time. And
all right. Thank you for everybody for coming. It's kind of interesting not to actually see you, although I can see little avatars.
Yeah. Thanks a lot. See you all at the next one.
Okay. Goodbye, everyone. Have a good day.